All right, so here we are in section 14.4, and what you're going to learn here is you're going to understand the definition and properties of a tree. You're going to find a spanning tree for a connected graph, and you're going to find the minimum spanning tree for a weighted graph. So a graph with the smallest number of edges that allows all vertices to be reached from all other vertices is called a tree. Now, graphs that are trees are shown below. So as you can see, I can go from A down here in the bottom over right here, all the way up and all the way over and all the way back down to G. So no matter what I need to get to, I can go from A to whatever other letter. Same goes with this graph, how it's shown. I can go from A to C or A to E or A to B, and then it just has to traverse different paths. And for this one, again, I can go down. This looks more like a family tree kind of graph, but this is another way that we call a tree, and hence family tree, and that would be what we would have. Now notice each graph is connected. This is a requirement because we must be able to reach any vertex from any other vertex. Furthermore, no graph contains any circuits, so we can't go and do a circuit and get back to where we started from. This is because vertices must be reached with the smallest number of edges. So if there's more edges, we need to actually delete those edges to make it actually a tree. Now, the below graphs are not trees. These circuits are actually our circuits, and they create redundant connections. So if we take away each of the redundant connections and all the vertices can still be reached from the other vertices, then we can get our tree back. And so if we look at this one, the first one, if we delete this piece here, that would get us back to our original tree that we had before. We could go all the way from A all the way over and down over here. But this, when we get back over here, we're starting to get more of a circuit, and that makes it a redundant. We need to delete that, and we could still reach all vertices. Now, same way here, this one, we have to delete this edge, the BC edge, because again, it's going to make us able to have a circuit, and we don't want to have that. Now on this one, probably the best one is this FC edge. Now, does that mean it's the only one? No, maybe we could have done the FB as well. It all depends on how your tree is set up and what the paths are. And so in this case, we're going to get rid of that one. So no, a connected graph has at least one path between each pair of its vertices. Because a tree has exactly one path joining any two vertices, it's connected. Now, by contrast, a complete graph has an edge between each pair of its vertices. So a tree is not going to be a complete graph. So if we had a complete graph, we'd have some extra edges and stuff here that we don't have. So a tree is not going to be a complete graph. All right, so some definitions and properties of a tree. So a tree is a graph that is connected and has no circuits, and all the trees have the following three properties. There is one and only one path joining any two vertices. Every edge is a bridge. Now think about that one. If it means, if we go back to our one here, any of these edges, we take them and delete it. So if we delete this DC, that means we're going to end up with two pieces, two components. We're going to have this component over here, and we'll have this component here, and they're not connected. So each edge is going to be basically a bridge. So that's going to be kind of a key there. And a tree with n vertices is going to have n minus one edges. We're going to have one less edge than we have vertices. Now, property 3 is a numerical property of trees that relates the number of vertices and the number of edges. So the total number of edges is always one less than the total number of vertices. For example, a tree with 5 vertices better have 5 minus 1 or 4 edges. Now, if we look back here, we have 1, 2, 3, 4, 5, 6 edges. So we better only have 6 vertices, so we should only have 5 edges. 1, 2, 3, 4, 5. Same thing here. We have 1, 2, 3, 4, 5, 6, 7, 8 vertices. So we have 1, 2, 3, 4, 5, 6, 7 edges. Same thing here. We have 1, 2, 3, 4, 5, 6, 7 vertices, and we have 1, 2, 3, 4, 5, 6 edges. So that's being followed, and that's kind of one of the key definitions that we need to follow, and it's going to help us figure out if we have the right number of edges or not. So, which graph in the below is set in the below set of 3 of them is a tree, and explain why the other 2 graphs are not trees? All right, well, let's look here. In this first one, notice we have a piece here and we have a piece here. So we have 2 components, right? So because we have 2 components and they're not connected, this is not connected, so that's not a tree because it's not connected. Okay. Now what about this one? Well, here we can go and we follow it, but notice we end up having this circuit down here. So because we have a circuit, it's not going to be a tree either. So it's a circuit, so not a tree. Now, how could we make this one a tree? Well, we could add that line in maybe, for instance. How could we make this one a tree? Oh, we could delete that line, for instance. Now, how about this one? Well, this one, it goes from any point to any other point or any other vertex, and this one would be a tree. Okay, so yes, that one is a tree. The other one is not because A, this would be a circuit, and B, this one was not connected. All right, so let's stop there and then we'll come back and we'll have talking about subgraphs.